Hello, and welcome to this presentation, Getting Started with the EVS1000 NDB mode. In this presentation, we'll show you how to make measurements of non-directional beacons using Rohde and Schwarz EVS1000 series analyzers. This presentation assumes a basic understanding of automatic direction finding, or ADF, and how this is used to locate non-directional beacons, or NDBs. It also assumes a basic familiarity with Rohde and Schwarz EVS1000 series analyzers. If you're unfamiliar with either of these topics, or if you'd like a review, you might want to watch the presentation Understanding ADF and/or Getting Started with the EVS1000 General Overview before continuing with this presentation. NDB analysis is enabled by software option K7 and provides information on signals from non-directional beacons. Note that these measurements are made using the EVS's low-frequency, or LF connector, rather than the RF connector used for most other measurement modes. Measurements include both the parameters of the identification signal, as well as measurements of distortion and harmonics. Measurement data can also be recorded for viewing on the EVS or for external analysis. Note that NDB analysis is only supported for EVSg and EVSf models. To access NDB analysis mode on the EVSg1000, simply press the Mode hard key on the front of the instrument and select NDB. If operating the EVS over VNC, press M, and then use the down arrow to scroll through the list of available analysis modes. Pressing the Config hard key or using S in VNC mode allows the configuration of two important parameters for NDB analysis. The first is a level unit, which can be toggled between dB microvolts and dBm. The second is the ID frequency, which can be set to either 400 Hz or 1020 Hz. This must match the frequency used by the measured NDB. And as mentioned earlier, please keep in mind that NDB measurements are performed via the LF-in connector. This is different from most of the other measurement modes on the EVS. The first step in NDB analysis is entering the beacon frequency in kHz. Globally, NDBs normally operate in the frequency range of 190 to 1750 kHz, although in the United States, the upper frequency is limited to 525 kHz to avoid interference to the AM broadcast band. To change the frequency on the EVSg, press the Channel Frequency hard key. In VNC mode, use the keyboard shortcut Q to enter the desired NDB frequency. NDB measurements are divided into three views on the EVS. These are ID, distortion, and recording. We'll start by looking at the ID analysis view. The NDB ID analysis view is divided into three sections: the level and frequency display, which provides information on the power and frequency of the received signal, the IF spectrum view, which shows power as a function of frequency, and the main numerical results view. We'll start with the level and frequency display. As mentioned earlier, the level and frequency display shows the power and frequency of the input signal, with power shown as an absolute value in dBm, and frequency shown as an offset in Hz from the nominal or configured NDB frequency. The bar graph shows the overload state. Green means no overload, yellow indicates an approaching overload, and red indicates that an overload is occurring. If an overload condition does occur, different messages will appear depending on the type of overload. For example, here both RF and ADC overloads. Regardless of the cause of the overload, the solution is to reduce or attenuate the input signal, and this can be done by setting RF attenuation to either normal or low distortion. Please see the EVS1000 General Overview presentation for more details on configuring RF attenuation. The IF spectrum preview provides a plot of power versus frequency, similar to a spectrum analyzer display. The center of the display, or the zero frequency, is the nominal NDB frequency, and the frequency range, or span, is set to the measured bandwidth. The EVS chooses a power range that will display both the peak and the noise simultaneously. The main application of the IF spectrum preview is verifying that the measurement settings are appropriate. For example, we can use the IF spectrum to see if an NDB signal is present, or if there's noise or other types of interference in addition to the NDB signal. Additional NDB signal analysis can be performed using AF spectrum and/or AF time domain modes. These are covered in separate presentations. Note that when switching to one of these modes, the current settings, such as the tune frequency, are transferred to that mode. Information about ident signal parameters can be seen in the ID analysis view. The time since the last received ID is shown, as well as the decoded Morse ID code and the period or interval between ID signals. The change in carrier level during transmission is also given. The length and spacing of the dots and dashes in the Morse ID can be seen along with the modulation depth of the ID signal. And finally, the frequency of the ID signal is displayed. Note that this should match the configured value, that is either 400 or 1020 Hz. The NDB distortion view shows various distortion factors for the beacon ID signal. As before, these can be analyzed at a configured beacon frequency of either 400 or 1020 Hz. Measured parameters include the AM modulation depth of the beacon ID, as well as information on harmonic distortion. The distortion for the second, third, and fourth harmonics is given individually, as well as the total harmonic distortion for all harmonics. And lastly, the parameter unwanted AM is a measurement of spurs within the antenna switching range. The last view we'll look at is the recording view, which displays and stores NDB measurements in tabular format. If GPS data is available, this data is also stored with the NDB measurement data. Data is stored with so-called status flags. For example, the M flag indicates a received Morse identification. Please see the separate presentation, Getting Started with the EVS1000 data recording, for more details and step-by-step instructions on logging and exporting measured data. In this presentation, we've covered NDB analysis mode, which is enabled by software option K7. This option performs both ID analysis and distortion measurements on NDB signals. Remember that unlike most other EVS1000 analysis modes, NDB signals are connected via the LF or low frequency connector. Additional displays of the received signal level and frequency, as well as a spectrum view, can be used to verify the presence of the NDB signal and/or the presence of other signals or noise. All measurement data can be logged together with GPS time and position information. And finally, configuration of NDB analysis is very easy. Simply enter the NDB frequency and configure the frequency of the ID signal. This concludes our presentation, Getting Started with the EVS1000 NDB mode. If you'd like to learn more about the EVS1000 or other avionics-related topics, please see the links in the video description. Thanks for watching.